All right, so these first two are going to be squeeze theorem problems, and the whole quiz is multiple choice. And so you don't have to worry about wording everything perfectly, writing everything perfectly. I'm going to go ahead and write it the right way, but it's okay if things get a little bit off, I guess. So for this first one, if we know that F is falling in between H and G, that's going to be kind of a hint that we're going to use the squeeze theorem to find the limit. So I'm going to find this limit, or try to, I might not be able to, by finding the limit as x approaches 1 of g of x and limit as x approaches 1 of h of x, and if they're the same, I automatically know that's the limit as x approaches 1 of f of x. If they're different, then I know it cannot be determined. So when I plug 1 in for g, we're just going to do this by direct substitution. The cosine of pi over 2, you can do a couple of ways. You can do the hand trick. Pi over 2 corresponds with your thumb, and so for your thumb, it would be the square root of the top fingers over 2, and there are no fingers above your thumb, so it's 0. So that 0 plus should be a 3. 0 plus 3 is 3. Okay. And then the other one is somewhat tedious because you have all those fractions to deal with, but when we're just plugging in 1, all we have to do is add and subtract the fractions. This is without the calculator, so you would need to find a common denominator. So that's going to be 10/4. Now, obviously, 3 does not equal 10/4. And so what you would choose, the answer you would choose would be cannot be determined. So I messed up. This should have been H. So that means the limit as x approaches 1 of f of x cannot be determined. Okay. Number 2 is the same type of question. So we're still finding the limit as x approaches 1. So we would do that for G and for H. And if they're the same, then that is the limit as x approaches 1 of f. So that gives us 10/2 or 5. Plugging in 1 again, super easy. All right, since they're both 5, that is telling us that the limit as x approaches 1 of f of x also has to be 5. If it's squeezed in between those, there's no space or any other number but 5. Okay. Number 3, you can use a calculator on it. I don't know if you really need it, but we have 3 and 4 are both rational functions, and we're deciding what type of discontinuity you can have. Now, a rational function has 2 types of discontinuity, a vertical asymptote and a hole. Now, that's not what the test is going to say. So for a vertical asymptote, it's going to say non-removable infinite. Discontinuity. All right, and then for the hole is going to be removable point. And there's a quick way to determine what that is by plugging in the value. If you plug in a value and you get something like a number like 5 over 0 or -7 over 0, that's going to be a vertical asymptote. if you plug in the number and you get 0 over 0, that's going to be a whole. So that's kind of a quick way you can make that determination. So for we're finding this for 1 and for -2. So for f of 1, you can use the calculator if you want to, but you would do 1 minus 4 is -3. My answer key, I have 5, but it's definitely -3. Right, and then for the denominator, 1 plus 2 minus 1 minus 2 is 0. So when that is the case, so that means x equals 1 is going to have a vertical asymptote or non-removable discontinuity. All right, and then for -2, f of -2, you could just use your calculator to plug that into the numerator, or you can do it in your head. It's completely up to you. Either way, when you plug in -2 in the numerator, you get 0. When you plug -2 into the denominator, you also get 0. So that means that x equals -2 has a whole, and that means it has removable point discontinuity. Right. Now you can also go to the graph to verify that if you want to, but a whole will not show up on the graph, but it will be an error on the table of values. All right, so we'll do the same thing for number 4. This time we're checking out when x is 4 and when x is -3. So f equals 4, we would plug it into the numerator, and we're going to get 7. We plug it into the denominator, we're going to get 0. That's the vertical asymptote or non-removable infinite. Discontinuity. I just realized I didn't write infinite on it when I did this one. Alright, and then when we plug in -3, we are going to get 0 over 0. So -3 is going to have a whole or removable point discontinuity. Okay. And then for 5 and 6, we're going to use this graph. So which values of x is the graph discontinuous, and identify the type. So right here we have a hole in the graph, and that is when x is equal to -2. And a hole in the graph is removable point discontinuity. So if it's all connected, but there's a hole in the flow of the graph, that's a removable point. All right, number 6 is kind of a confusing question. We need to know what table of values matches this graph. Now, one thing that I can tell for sure is that there is a point at -2, -1. This point is at -2, -1. So the answer table has to have a point at -2, -1. And this one doesn't. So A is not an answer choice. And this one doesn't. So D is not an answer choice. So then we need to look at the values that are close to the hole and figure out if they match B or if they match C. So close to the hole on the left side is just going to be slightly, or on the left side is going to be slightly larger than 2, and on the right side slightly smaller than 2. So that is going to be C. All right, number 7, we have this another graph, and we're going to determine where we have the different types of discontinuity. So number 7 is just asking for removable discontinuity. The only removable discontinuity is a hole that is in the flow of the graph, and that happens when x is 2. Okay, removable jump discontinuity is when we have a break in the graph similar to what we have right here, which is when x is -2. And then non-removable infinite is when there's a vertical asymptote, and to me, it looks like there's a vertical asymptote when x is equal to 0. All right, and then 10 is its own separate question. It doesn't have to do with that graph. It has to do with this table. And so the function g has properties indicated in the table. We want to know where g is continuous. So for a function to be continuous, at a point, it must be defined at that point, and the left and right hand limits must be equal, and they must be equal to what the value of the function is. So all three of these things have to be equal. The only time all three of those things are equal is when a is 2. Okay, number 11 comes back to our good old fractional absolute value function that hopefully one day you guys are going to get. So this graph I know for sure is going to have like a horizontal line at -1 and a horizontal line at 1. And whatever makes these numerator and denominator 0 is where it jumps. So this graph should look like this. And it is a jump discontinuity, and that happens at x equals 2. So it's a non-removable jump at x equals 2. Okay, all right, and then this one, we've got this crazy piecewise function, and we're trying to figure out if the graph is continuous at these points, which means that the left and right hand limits have to be equal, and they have to be equal to what the function is defined at that point. All right, so we have 0. So to figure out 0, so I'm going to just put over here, I'm checking x equals 0. We're going to find the limit as x approaches 0 from the left of f of x. Just by plugging in 0, we get -1. Right? That must equal f of 0, and f of 0 is 1. So there's no way it works. So that's a big no. All right? And then 1 falls in this range. All right, so in this range, I use the function 4 minus 1. 4 minus 1 is a continuous function. It's a linear function. So if we're falling in that range, we're definitely continuous there. All right, and then let's check x equals 2. So x equals 2 is a breaking point. So x equals 2, we would need to find the limit as x approaches 2 from the left of f of x by plugging in 2. So that's 8 minus 1 is 7. We would need to find the limit as x approaches 2 from the right of f of x by plugging in 2, and that's 4 plus 3, which is 7. And we would also need to find f of 2, which tells us right here that is also 7. So all those 7s match up. So we would say yes, the function is continuous there. Right? And then this last one, 4, isn't like a changing point. It falls in this range right here. So this is a continuous function, so it's automatically yes. So that's a different type of question right there. Okay, and then 13. 13 is this last step we did. So we have this piecewise function, and if f is continuous at x equals 2, what has to be the value for k? So first, I'm just going to double check that one of these at 2 has an or equal to bar, so that's good. It's possible for this to be continuous. So for the function to be continuous at x equals 2, the limit as x approaches 2 from the left must equal the limit as x approaches 2 from the right. And we'll just do direct substitution by plugging 2 in for x. So it's going to be 1 there and 6 there. So to me, it looks like k is going to be -5. Alright, so good luck on your quiz. I'll see you guys later.